Good morning, students. In the last class, we were discussing about the applications of biotechnology, and we have studied the various commercial products that we are producing using the E. coli and the plasmids, like the recombinant insulin, the human growth hormones that we have studied, then interferons. We also studied the blood clotting factors, age, how can be produced outside, that is in the E. coli. As well as we also studied the recombinant vaccines, especially we talked about the DNA vaccines. And today we are going to concentrate on another new topic called gene therapy. It's a beautiful topic where we will have the more job-oriented courses, and more advanced courses, that is the gene therapy. Okay. So for treating any kind of a disease, we used to take some medicines or some drugs. But for this gene therapy, this is meant only for some kind of hereditary disease. And today there is a great challenging that to cure a genetic disease is a great challenging today we are facing. Now, so this gene therapy is giving a kind of an option, or it is a method where the defective gene can be corrected so that that defective gene will not pass to another generation, and another generation will not have a kind of a hereditary disease or the genetic disorders or genetic diseases. And there are so many very serious hereditary diseases are there that is really going to affect the human beings, and the person who is being affected will be suffering a lot because of that genetic disease. And some children will die even in a kind of a disease called like thalassemia and all. The children will not survive after the age of 17. So all these are major problems that we have it, and that is because of the genetic disorders and genetic diseases. And this gene therapy is a fantastic kind of an approach for this kind of curing of the genetic disorders. And at present, most of the genetic disease has no effective treatment at all. Okay, most of the genetic disease you take, there is no effective treatment at all. And very method that is used for the gene, the defective gene is being corrected, or the hereditary disease is being corrected, is only by the gene therapy method. Okay, so now in the gene therapy method, what we are going to study is, we are going to study how a gene is being corrected, a defective gene, how is being corrected. So what we are doing is here, the gene therapy is talking about the correction of the affective gene. So if the affective gene is there, the affected gene, now this affected gene is being corrected by this kind of a gene therapy. So this is being corrected, or it is being rectified. So this gene therapy will always involve in the correction of the affective gene. For example, if you take the diabetes mellitus, this is also one of the hereditary diseases. It is because of some kind of an hormone deficiency, but that is also one of the hereditary disease, that diabetes mellitus. Okay, so what happened is, the person's beta cell itself is not synthesized. There is no beta cell. That means even the beta cell is there, the beta cell cannot produce the hormone called insulin. So that kind of a gene there is defective. So we are removing that gene which cannot produce a cell called beta cell, and we are giving a new gene so that the beta cell can be synthesized more, secreted, and it can also secrete a hormone called insulin. Now in gene therapy, the affective gene is being corrected. Okay, so what we are doing is, we are removing the diseased gene. The diseased gene is being removed, and we are inserting a normal gene in the place of the defective gene. So this kind of a method, that is removing the diseased gene and replacing with a normal gene, is always done by the vectors. Vectors are some of the plasmids. Here in the gene therapy method, we are studying the vector is the retrovirus. We'll talk about retrovirus later. Okay, retrovirus, HIV is a retrovirus. Especially when you talk about the retrovirus will have the genome called RNA. It do not have the DNA. It has the RNA in it. Okay, so we will talk talk about this later on, about when we talk about the vectors and all. So at timing, you remember, always the disease gene is being replaced by the normal gene by using the vectors. Vectors here are the carriers. So you insert the normal gene to the vector, so the normal gene is carried to the patient and the defective gene is being, or disease gene is being corrected. Okay, so that is the method. Now here in this kind of a gene therapy, the what kind of a disease is actually cured is, the disease which is cured is called a single gene mutation. Single gene mutation. That means, mutation means there is a sudden change in the genetic arrangement of the gene. Suppose if this is a genetic material, this is a DNA, and DNA will have the kind of a genetic code in it. So it has the adenine, thymine, guanine and cytosine. Always the adenine will be pairing with the thymine, and the thymine will be pairing with the adenine, and guanine will be pairing with the kind of cytosine, and the cytosine will be pairing with the guanine. So these are the genetic arrangement. Okay, so this is a normal gene. Now sometimes this normal gene will undergo a kind of a mutation. Mutation means change, sudden change in this genetic arrangement. Suppose if there is 1, 2, 3, 4, like this kind of a gene arrangement is there, there is a change. So that means instead of 3, one more 2 is added, and it continues with 3, 4, 5. So here you can find an additional gene, an additional kind of a genetic code or the nucleotide is being added. So this is an indication of the mutation. So this is what single gene, one gene, if it is undergo a kind of a changes in the genetic arrangement, that is called gene mutation. Now this kind of a gene therapy is done to correct this kind of a single gene mutation. Now, it's a very important public one mark question. Gene therapy is done to correct the single gene mutation. Genes can be corrected. Okay, so that is the idea of the gene therapies. Now, what are these diseases that is caused due to a single gene mutation? There are two very important diseases, that is called the hemophilia. Hemophilia is a disease that we have already studied. Is a venous disease where the blood will not undergo clot because the blood clotting factor 8 is not there in the blood of the patient. So this is a kind of a ADT disease, and this disease is caused due to a single gene mutation. And second one, the disease is called cystic fibrosis. The cystic fibrosis. So this is another disease. The cystic fibrosis is also another serious disease which will always damage the lungs and the digestive system. The lungs and the digestive system, these organs are endowed or covered with a membrane called mucus. That's what we studied. What happens in this disease? The mucous membrane, the role of the mucous membrane we have studied in the last year digestive system, as well as we have studied the immunology. This kind of a mucous membrane will protect the inner layers, inner organs, as well as it gives a kind of a lubrication. Now, this kind of cystic fibrosis disease will make the mucous material become more stronger, thick and sticky. So this will be causing a kind of a disease due to in the lungs as well as in the digestive system. Okay, so that is, so this kind of a disease are very serious disease. So this patient will die because of the damage of the lungs and diseases, and the hemophilic person will die because of the blood keep on bleeding, prolonged bleeding will be there, and internal organs also start bleeding. So that all these are the serious diseases which will lead to death. So these kind of diseases are caused by a gene, that is a single gene will undergo mutation. So these kind of a gene can be corrected by using a gene therapy. In gene therapy, what we are doing? We are removing this affective gene, the defective gene is removed and replacing with a healthy or a normal gene along with the vectors. Okay, so that is the idea of having the gene therapy. Now, when we talk about the gene therapy, we will have two strategies regarding this gene therapy. One is the gene augmentation. That is, first one is called the gene augmentation. So gene augmentation means that is increases. Augmentation is otherwise called as increases. Augmentation means here we are increasing the number of the genes. Now I'll give you a statement you to remember here. See, in the gene augmentation is always involved in the insertion of the gene. Very important sentence it is. You are introducing, so insertion of a DNA. The DNA is inserted into a genome. I'll tell you what it is. The DNA is inserted into a genome. Okay, genome, and this is done to replace. This is done to replace the missing gene, the missing products, the missing gene products. Okay, so the missing gene products. Now, so this is a statement that you have to study in the under the gene augmentation. See, what you are doing is you are going to insert the DNA. Okay, so in the genome, see the genome is very bigger, very lengthy. This is the genome. Now, what you are doing is you are going to insert a normal gene if this patient is being affected with a kind of a disease, a hereditary disease. Now, you are taking the genome, and you are taking and isolating a gene. This is a kind of a DNA. So, you are inserting the DNA into the entire genome. Okay, to replace. Why you are inserting? To replace the missing gene products. What are the gene products? See, I tell you, the gene, that is the DNA. Okay, gene means that is the DNA. The DNA will always undergo a transcription process. So this is the kind of a process called transcription process. Okay, so the gene will undergo transcription process to produce the RNA. RNA will undergo a kind of a process called translation process to give the proteins. So proteins going to give the going to function or going to perform a function. So all the function that is performed in the body is only by the proteins, and these proteins are all coming from this kind of a single kind of a DNA that is residing in the cells. Okay, now this missing gene products, that means the protein, that is the protein and the function that is related to the protein, all these are the gene products. So the protein is a product of a gene, and the function that is prescribed to the protein is also a product of a gene. Okay, now the gene will undergo transcription to form RNA, and the RNA will undergo translation to form the proteins. Clear? Right. Now, another concept here, one more thing you remember, in gene augmentation cases, in one cases of gene treatment, genetic treatment, this DNA cannot produce the protein. That is what. So now in the patient who is having some cases, not all the cases, in some cases, that is in one case, the patient is suffering from kind of hereditary disease. So this patient cannot produce the proteins. The protein is not produced. So that is the missing gene products. So the protein cannot be produced. So gene is missing their own products. So to make this gene to produce the protein, you are inserting a DNA into it. Okay, this is a normal DNA. When the normal DNA, if you insert into a patient genome, now this DNA can able to produce, this DNA can produce the proteins when after the normal gene is being introduced. When the normal gene is introduced into the patient, now through the vector, now the normal gene can produce the proteins, and the protein can able to do the functions. Okay, so that is one. So introducing a gene, so that can translate. The gene can able to undergo transcription, and it can able to translate to produce the protein. Okay, so this is how the gene augmentation is done. So increasing the gene products. That is what gene augmentation. By using the gene, you are increasing what? You are increasing the gene product, that is a protein, and this protein this protein can produce more number of the products. Okay, so this is the entire product. So now if this protein is not synthesized, the blood clotting factor is not there. Now you are introduced a new gene. Now the protein is prescribing the function, so the blood clotting factors can produce in the human body, and the hemophilia is being entirely eliminated, or it is being removed or treated with a gene therapy. So that is one part of the gene therapy, that is called gene augmentation. And second one, the second strategy we talk is the gene inhibition. That is the second one, that is the gene inhibition. This is the second strategy, that is called gene inhibition. Now, this is what the another word strategy of the gene therapy. One is the gene augmentation, another one is the gene inhibition. In gene inhibition, the word itself you can very clearly understand. So gene is going to inhibit, gene is going to stop. Now, what you are doing is sometimes, see, in one cases the gene cannot produce the protein. So you are replacing the gene and giving the gene so that a protein is being produced. In other cases, what we are doing is the gene can produce the protein. See, the DNA can produce the protein, but this protein is overactive. That is what very important. Overactive. That means it is producing more number of the limited. So it is overactive. So what we are doing is we are giving a gene to inhibit that overactive part. So what we are doing is we are using in this genome we are placing a gene called antisense gene. Antisense. Okay, so this gene, antisense gene, we are introducing into it. So this antisense gene will recognize the dominant gene which is there inside the patient. So the dominant gene is responsible for overactive. So when you give the antisense gene will inhibit the dominant gene, so the protein is not overactive. Okay, so these are the two strategies of the gene therapy. One is the gene augmentation and other one is the gene inhibition. Clear? Right. So next we'll talk about the gene therapy is done in two different cells. Okay, one is the somatic cells and other one is the germ cells. Okay, somatic cells. Gene therapy is done in two cells. One is the somatic cells and other one is the germ cells, that is called the reproductive cells. So germ cells or germline cells. So reproductive cells. So there are two things in two cells the gene therapy is done. Somatic cell is also called as body cells. These are body cells, and that is called the reproductive cells. This one is the reproductive cells. Okay, so reproductive cells. This is the body cells, and the germ cells are the reproductive cells like egg and ovum. Okay, right. Now in somatic cells, the gene will be transferred into the somatic and germ cells, and the cells that is being used. So the gene will be transferred to the cells, taking the gene and giving to the cells. Okay, so taking the gene and giving to what are the somatic cells? There are three cells are there. One is the blood cells, some skin cells and bone marrow cells. So you are using the gene is taken and the gene is introduced into these kind of somatic cells like blood cells, somatic cell, that is the skin cell and the bone cells. Whereas here this is given to the reproductive cells like egg and the sperm cells. Okay, right, the gene is taken and introduced into the somatic cells, and there it is to the germ cells. And the gene therapy that you have done it in the somatic cells will not pass to another, it is not heritable, that is, it is not passed to another generation. It is not passed to the another generation. Okay, whatever it is corrected, only for that particular generation alone, it is not passing. But whereas, whatever you do, you are doing it in the egg and sperm. So, it will pass to another generation. It will go to another generation. So, that is the germline gene therapy. Okay, and the last one is here you are going to insert the gene, that is fully the functional gene, old gene is being introduced, old gene, that is going to be the whole genome, that is the fully functional and expressible gene can be sent into it, old gene. But whereas you are in germ cells, you are introducing the DNAs. like this. So you're introducing the DNA. This is the whole gene itself you are putting inside, and that you are sending the particular DNA inside. So that is the difference between the somatic cells and the germ cell gene therapy. Okay, now we are going to study how this gene therapy is being corrected for various diseases, and especially we are going to talk about the disease called SCID and how the disease is corrected by using this kind of a gene therapy. Okay, fine. So now we'll study a disease called SCID. SCID. SCID is also called a severe combined immunodeficiency disease. So it is SCID is a disease that is being cured by using gene therapy. Now this disease is also called as ADA deficiency. ADA means adenosine deaminase deficiency, an enzyme. So now we are talking about the disease called SCID is being corrected by using a gene therapy. Now the SCID is also called as ADA, that is adenosine deaminase deficiency. That is adenosine, it's an enzyme. Okay, adenosine deaminase is an enzyme. Okay, now the patient who is suffering from this disease, SCID, is also called as bubble boy syndrome. Okay, for children it is being affected. Now, the patient who are suffering from the disease called SCID, the enzyme called adenosine deaminase will not be synthesized. There is no enzyme called there is no enzyme called adenosine deaminase. So the adenosine deaminase enzyme is undergoing deficiency. Okay, right. Now we have to talk about what is the major role of this adenosine deaminase deficiency. Why? If it is not there, what is happening? So now we are focusing a disease called severe combined immunodeficiency. Immunodeficiency means if you have this kind of a disease, overall immune system is reduced in your body. Your body WBC all will be reduced. So you will not have any immunity at all. So your body immunized is done by an enzyme called adenosine deaminase. If this enzyme is not synthesized, okay, you will have a serious defect in the body's immune system. Your T cells cannot function properly. So you will have a kind of, then this disease will lead to death. Okay, so that is the responsibility of an enzyme called adenosine deaminase. And if this enzyme is not there, we will have either adenosine deaminase deficiency syndrome or otherwise called as SCID disease, severe combined immunodeficiency disease. Okay, right. Now, this disease is a autosomal disease. Autosome means this disease is caused by your body chromosomes. There are two chromosomes that we have two set of chromosomes. One is the autosomes, another one is the allosomes, that is body chromosome and the sex chromosomes. So this disease is caused by the autosome as well as recessive gene. Recessive means there are two sets of alleles we have. One is the dominant, another one is the recessive. So here, if this disease happens because of the recessive alleles, two recessive alleles, that is either small t or small t, whatever it is. So it happens because of the two recessive alleles. So it's an autosomal recessive allele or metabolic disorders. Metabolic disorder means we will talk metabolism for the enzymes. So this enzyme called adenosine deaminase is not there. So the metabolism process is not happening. So this disease is called autosomal recessive mutation disease. Now the patient who are affected with disease will have either deletion or the dysfunction of producing the ADA enzyme. This enzyme is produced by certain genes responsible. So this gene is called ADA gene. So this gene will produce an enzyme called adenosine deaminase. Okay, adenosine deaminase. Okay, so this gene is responsible for producing, that is ADA gene is responsible for producing this enzyme. The patient who are suffering from this SCID will not have this gene, so they cannot produce the enzymes called adenosine deaminase. Okay, now in this case, what happens is the T lymphocyte always fights with the viral infected disease. So the T cells here in this disease, the T cells cannot produce the immune response. That is, the immune response are not produced. The body is not fighting with the microorganisms, so it is not produced. The T cells cannot produce the immune response because of this. Okay, so now we are undergoing a kind of a treatment. How this patient can be cured from this kind of a SCID. So how we can make the patient to make the gene to produce adenosine deaminase enzyme. So what we are doing, we are going for gene therapy. We are removing the gene which cannot produce this enzyme and giving a new gene in place of the defective gene, so that gene can be able to produce the deaminase, adenosine deaminase. So now the patient T cells all can be activated and can be able to produce gene immune response. Okay, one diagram part is there that I will explain to you when the Zoom class is there, and this part I will just complete it. Okay, now this kind of a clinical gene therapy was done in 1990s by French Anderson, and he has done this kind of a gene therapy with a 4 years old girl child. This kind of a gene treatment is done. Okay, so this treatment is done for a girl who was affected with kind of a disease, and that girl's age was 4. So he was done this kind of a treatment in the 4 years old girl child who was affected with kind of a adenosine deaminase deficiency. Okay, right. So what they have done now, so that is what that you will have in the book in the tablet column. Afterwards you can study this kind of a content. I just talk to you now. Now this deaminase deficiency may be varying from one person to another, the treatment. So in some, now we are going to talk about how this can be treated, and the procedures will stay after. First we talk about the treatment. Okay, now for some persons, for some, not for all, for some, the adenosine ADA, that is adenosine deaminase deficiency, can be cured by removing or by transplanting the entire bone marrow. So bone marrow transplantation should be done. Transplantation. See, transplantation means you remove all the bone marrow. Okay, especially if it is affected for the children. Okay, children will be affected with this kind of a disease. That is why the 4-year-old girl child is also being affected. Now, when the child is being affected with this disease, you remember all the T cells will not function. Okay, and T cells cannot produce immune response, and we have studied thymus gland, all the T cells at all. The T cell remain active only up to puberty. After the puberty, it stops its function and it atrophies, it decreases in size. In adults, cases, the T lymphocytes are very less because thymus gland is keep on shrinking as the age progresses. Okay. So, if the child will be suffered from this kind of disease, T cells are not liberated and cannot respond to the microorganisms. So, you remove the bone marrow. Bone marrow has to be transplanted because bone marrow is the site for the production of the RBC and WBC. All blood cells are produced in the bone marrow. Okay, and so this bone marrow, if you remove, because this bone marrow is useless, it cannot produce the blood cells. WBC cells cannot be produced. So you remove the entire bone marrow from the child and give the new bone marrow so that the child have the chance of surviving. So this is what done for the 4-year-old girl child who was affected with this kind of a disease, and the child's bone marrow was completely removed and it was replaced. So that was a treatment. There's one of the treatment, and this is for some people it can be done. And for other treatments, for some, you have to give an enzyme replacement therapy. That is, what is that enzyme replacement therapy? That is enzyme replacement therapy. So enzyme replacement therapy means you are giving a functional ADA enzyme, ADA gene. That means you are injecting to a patient. You give an injection to the patient with this kind of an enzyme. That is a functional enzyme. Enzyme is adenosine deaminase. This enzyme is being given to the patient in the form of injection. So enzyme is being replaced. Okay, so this is one kind of a treatment. But all these are not permanent treatments. So what is the permanent treatment? That is what the permanent treatment. The permanent treatment for SCID. The permanent treatment is ADA is isolated from the bone marrow. ADA means that is that is the gene that is responsible. So if you take the bone marrow, if you see the bone marrow can able to produce the WBC, all this, Now, so there will be a gene responsible to produce all this. So that gene is called adenosine deaminase. Now, this gene is located in the bone marrow. So you isolate this gene, and after isolating, you are injecting this gene or introducing the gene into the cells. Okay, to the cells of the patient. So you are giving the cells. The cell is an embryonic stage. That is when the embryo is undergoing development, that is the womb of the mother. This kind of a gene is taken from, because hereditary disease can be easily found out when the child is in the womb of the mother. If the parent or the family members, anyone is affected with the kind of a disease, there may be a chance of the disease spreading to the young ones. So there is a kind of a karyotyping treatment and all. So in karyotyping, you can know whether the child is being affected or not with the genetic disease, and you can very easily picturize whether which gene is affected. So if you find that ADA gene is being affected and the child is going to be suffered from SCID after the child is born, so you can take the gene from the bone marrow of the normal patient and you can insert into the cell of that baby in the embryonic stage. So that gene will incorporate it into that, and now the gene can be able to produce that kind of an enzyme. Okay, so this is an idea of the replacement of this kind of a gene. So this kind of treatment is a permanent. Removing the bone marrow and transplanting is how much it works is a question mark. As well as if you give the enzyme replacement therapy with the injection, this is also a question mark how much it is going to work. So the permanent treatment you can solidly build it by taking an entire gene from the bone marrow and give it to the patient, and now the patient, that is also you are giving to the embryonic stage itself, so that as the embryo is growing, the gene also grows and does its own function, can translate as and transcribe to RNA and translate into protein, and that can function, and the adenosine deaminase can able to synthesized. Okay, so now the T cells can be done. So all these are the product that we have done it, the treatment that we have done it in the gene therapy. Now the final part what we are going to discuss is in gene therapy, how the process is done. The process actually done is the process of gene therapy, the stages, the process. Now in process, what we are going to do is we are taking the patient blood. Okay, we are taking the patient blood. We are going to do gene therapy. So first stage, you are removing the blood of the patient, and in the blood, after removing the patient blood, you isolate in the blood. You are going to isolate the lymphocytes. Lymphocytes in the sense the T cells. T cell, B cell are called lymphocytes. So you take the patient blood and you isolate the lymphocyte. Now these lymphocytes are grown. They are grown in the culture medium in the laboratory. That means you take a petri plate, you pour some nutrition and place all these lymphocytes, T cells inside and making the T cells to grow. Okay, so T cells are growing. So isolate the lymphocyte and it is growing in the culture medium. Okay, now as it is growing, the anti-functional ADA and cDNA are going to introduce it. So now in this culture medium, you are introducing two things. One is a functional gene for ADA. That is, ADA gene is introduced into it. Second one, you are introducing cDNA. cDNA is otherwise called as complementary DNA. Okay. Now you are introducing two things to this culture medium. What you have done, you have removed the patient blood and you are isolated the lymphocyte T cells, and the T cells are growing in the culture medium in the laboratory. Where as it is growing, you are introducing two things. The gene which is responsible for producing the enzyme called adenosine deaminase. Then you are inserting a cDNA, is a complementary DNA. Now what is after doing this DNA will make this kind of, it will incorporate, it will take up this gene and this can convert into, the cDNA will form the mRNA, it's a messenger RNA. Okay, so the cDNA will send a message to the mRNA in the form of a transcription of this. Then again this mRNA can build the DNA, and the DNA further will undergo RNA, all this. So finally it can able to produce proteins. protein can able to produce an enzyme called adenosine deaminase. So this is an enzyme, adenosine deaminase. This enzyme is produced by this protein. So this cDNA will take up this gene, will accept the gene, and the gene message is sent. The cDNA will read that information, and the information is sent to the RNA in the form of a message. So now this RNA will synthesize the protein by carrying the message that is having the gene called ADA, and now this mRNA can be able to synthesize the proteins. Okay, now this introducing these two things. Okay, you have taken the functional gene and the cDNA and introducing into them. Then all this introducing is done by using vectors. By using the vectors. So here we are using a kind of a retrovirus. So then this kind of this T cells, now the lymphocyte is there, the T cell. Now the T cell will have the gene that is responsible for causing, that is the ADA. So this can produce an enzyme. Okay, so this T cell which has cultured there can, before it was, this T cell cannot produce, before the T cell cannot produce that enzyme because that kind of a ADA gene is not there. Now purposely you have introduced the gene into this T cells. Now the T cell is carrying that gene. Now this, if you give to the patient, this T cell now can be able to synthesize the enzymes, and because of that enzymes, all this kind of immunity is being gained. Now this kind of adenosine deaminase deficiency, by using the enzyme, this can produce more number of lymphocytes, and the lymphocyte can be able to show some immune response. Okay, so this gene produces enzyme, and the enzyme produces the further T lymphocyte, and the T lymphocyte will involve in the immune responses. Okay, so these cells are, and very important is, these cells are not mortal. Whatever you produce, it is not undergoing death. So patient required always one thing in this treatment is the T cell which is there, it is not immortal. So that means it will die afterwards. Okay, whatever it is produced, it will die, keep on. In one cycle, it will die, keep on dying. So the patient requires a periodical transfusion of. So often he has to go for this kind of a treatment. That means this is a prepared, already ready-madely prepared and kept. That is, this culture is done and kept already. So the patient should go to the particular doctor, and he has to take this kind of a T lymphocyte, that is the specialized T lymphocytes he has to take, and it is immortal. It is not immortal. That means it will undergo kind of a death. Once again it will destroy, and once again you go, and again you have to periodically. So continuously, not continuously. So one cycle is complete, again go. So periodically you have to take the transfusion of this lymphocytes. Okay, so he has to keep on do this. Okay, so that is the treatment. So if you do all this, the patient will not be suffered from kind of a SCID, because SCID is a very serious disease. Okay, it's a severe combined immunodeficiency. Is also called as bubble boy syndrome, where the child's all WBC will be drastically reduced, and if this WBC is not there, the child will be affected with very serious infections. Any kind of a disease, infected disease will affect that particular person, and the child will not last for more than 10 to 15 years. After that, he will not survive. So in that case, this has to be considered as a very serious disease, and the gene therapy is an excellent option for this kind of treating this kind of diseases. Okay, right. So now I told you there are vectors here we are using. Is the retrovirus is a vector that we are using here. That is a retrovirus. Retrovirus here, the genetic material of the retrovirus here is, we have the RNA as the genetic material. The RNA will be undergoing, again here is a DNA. Normally the DNA will undergo RNA, but here the RNA will undergo a kind of a changes, that is cDNA. So this is taking place in the reverse matter. So it is done by a process called an enzyme called reverse transcriptase enzyme. Reverse transcriptase an enzyme. So this is what we have studied in the HIV and all. In AIDS, we have studied the retrovirus and all. So this is another topic, and one part is left over. Some diagram I have to explain it. That diagram I will do in your Zoom app class. So far we have studied what is gene therapy and what are the two strategies, that is gene augmentation, as well as we have studied the gene inhibition. Then we have studied the somatic cell and germline gene therapy differences. Then also we have studied how can the SAID or adenosine deaminase deficiency disease can be cured by doing this kind of a gene therapy. In the next session, we will study about the stem cells. Clear? Right. Thank you.